October 14, 1944, 13:47 hours, 180 miles northwest of Luzon. The Kamikaze pilot diving toward USS Randolph had calculated everything perfectly: his angle of descent, the ship's evasive maneuvers, even the timing of American anti-aircraft fire. What he hadn't calculated was that American shells would now explode within 70 feet of his aircraft without ever making contact. The Japanese High Command had dismissed intelligence reports about this impossible American technology as propaganda. They were about to pay the ultimate price for that fatal miscalculation. The morning sun cast long shadows across the Philippine Sea as Admiral Takeo Kurita's Northern Strike Force approached what Japanese intelligence believed would be a decisive victory. For 18 months, Imperial Navy pilots had been reporting impossible occurrences: American anti-aircraft shells that exploded in perfect proximity to their targets without direct hits. Japanese military scientists had analyzed captured shell fragments and dismissed these reports as combat hallucinations or propaganda designed to demoralize pilots. Lieutenant Commander Hiroshi Yamamoto, leading the third wave of kamikaze attacks that October morning, had been briefed on American defensive capabilities based on traditional ballistic calculations. Japanese tactical manuals, updated as recently as September 1944, assumed American anti-aircraft fire followed conventional patterns: shells that exploded only upon impact or at predetermined time intervals. Their attack formations had been meticulously planned around these assumptions. The reality emerging from American cruiser formations would shatter 3 years of Japanese tactical doctrine in less than 3 minutes. What the Japanese High Command had failed to comprehend was that American scientists had solved one of warfare's most complex problems: how to make an artillery shell think. The proximity fuse, designated VT in classified documents, represented a technological leap that Japanese military leaders considered physically impossible given the constraints of 1940s electronics. The device packed into each 5-inch shell contained miniaturized radar equipment that could detect nearby aircraft and trigger detonation at optimal range. This wasn't theoretical technology. By October 1944, American factories were producing proximity fuses at a rate of 100,000 units per month, each one containing innovations that Japanese scientists wouldn't achieve until years after the war's end. Admiral Kurita's attack plan, developed by the Imperial Navy's most experienced tacticians, had accounted for every variable except the one that mattered most. Japanese pilots had been trained to exploit gaps in defensive fire patterns, to use evasive maneuvers that had proved effective against conventional time-fused shells. Their attack formations had been meticulously planned around these assumptions. The reality emerging from American cruiser formations would shatter 3 years of Japanese tactical doctrine in less than 3 minutes. The fatal underestimation was about to extract its price in ways that would transform naval warfare forever. The strategic situation facing American naval forces in late 1944 had become critically dangerous. Japanese kamikaze tactics, first systematically employed during the Battle of Leyte Gulf, had achieved unprecedented success rates against American ships. Traditional anti-aircraft defenses, designed to combat conventional bombing attacks, proved inadequate against pilots willing to sacrifice their lives for guaranteed hits. Statistical analysis from Pacific Fleet Headquarters revealed the sobering mathematics of kamikaze warfare. Conventional anti-aircraft guns achieve hit rates of approximately 3% against diving aircraft. Even when hits occurred, single projectiles rarely possessed sufficient destructive power to stop a determined suicide attack. Japanese pilots had learned to approach from multiple angles simultaneously, overwhelming defensive fire through sheer numbers.
Captain Wesley Harrison, commanding the anti-aircraft cruiser USS Oakland, had filed report after report documenting the inadequacy of existing defensive systems. His ship's battery of 16 5-inch guns, considered state-of-the-art in 1942, could engage only limited numbers of targets simultaneously. Time-fused shells required precise range estimation and perfect timing, calculations that became impossible when facing multiple high-speed maneuvering targets approaching from different vectors. The Japanese had studied American defensive patterns meticulously. Captured documents from downed reconnaissance aircraft contained detailed analyses of American gunnery procedures. Japanese tactics exploited the fundamental limitation of conventional artillery. Shells exploded either on impact or at predetermined time intervals, creating predictable defensive patterns that skilled pilots could exploit. Imperial Navy training manuals, updated based on 18 months of combat experience, taught specific techniques for defeating American anti-aircraft fire. Pilots learned to approach during the vulnerable seconds when gunners reloaded, to use evasive maneuvers that forced Americans to waste ammunition on empty sky, and to coordinate attacks that arrived simultaneously from multiple directions. Japanese losses mounted steadily throughout 1944. USS St. Lo had been sunk by a single kamikaze hit. USS Princeton suffered catastrophic damage when conventional defensive fire failed to stop a diving bomber. Fleet Admiral Chester Nimitz's operational reports documented increasing concern among ship commanders who felt helpless against tactics that seemed to guarantee enemy success. The problem extended beyond individual ship survival. American amphibious operations required sustained naval gunfire support, but ships forced to maintain constant anti-aircraft vigilance couldn't provide effective ground support. The entire Pacific strategy risked stalling as naval forces diverted resources to defensive measures that weren't working. Japanese intelligence services, meanwhile, had concluded that American defensive capabilities had reached their technological ceiling. Reports from submarine reconnaissance and captured personnel indicated that American gunners were already employing their most advanced fire control systems. Japanese military scientists calculated that physical limitations of conventional artillery made significant improvements impossible. This assessment would prove to be Japan's most costly intelligence failure of the Pacific War. While Japanese tacticians congratulated themselves on developing unstoppable attack methods, American scientists had been working in absolute secrecy on technology that would make every assumption about aerial warfare obsolete. The solution already existed in American research facilities, but its deployment remained weeks away from the desperate naval commanders who needed it most.
The weapon that would revolutionize naval warfare had been born from a collaboration between Johns Hopkins University's Applied Physics Laboratory and the National Defense Research Committee in early 1940. Dr. Merle Tuve, leading the proximity fuse development team, faced an engineering challenge that seemed impossible: creating a miniaturized radar system capable of surviving the violent acceleration of artillery fire while maintaining sufficient sensitivity to detect aircraft at combat ranges. The technical specifications documented in classified Navy Department records revealed the revolutionary nature of the VT fuse. Each unit measured only 5.5 inches in length and weighed 2.1 pounds, yet contained a complete radar transmitter, receiver, antenna system, and electronic firing circuit. The device operated at 180 to 200 MHz, transmitting continuous radio waves and analyzing reflected signals to determine target proximity. Initial development at the Dahlgren Naval Proving Ground in Virginia had overcome seemingly insurmountable obstacles. The fuse's vacuum tubes needed to withstand accelerations exceeding 20,000 times the force of gravity during gun firing. Standard electronics of the era would have been destroyed instantly, but American engineers developed specialized shock-resistant components using innovative mounting systems and ruggedized tube designs. The detection mechanism operated on Doppler shift principles, analyzing changes in reflected radio frequency to calculate target distance and closing velocity. When an aircraft approached within the predetermined kill radius, typically 50 to 70 feet for 5-inch shells, the fuse triggered detonation automatically. This created a lethal fragmentation pattern with a 95% probability of inflicting fatal damage on any aircraft within the blast zone. Production challenges had required unprecedented industrial coordination. The Eastman Kodak Company manufactured the fuse bodies, Sylvania produced the specialized vacuum tubes, and Western Electric assembled the electronic components. By October 1944, American factories were producing proximity fuses faster than shells could be manufactured to contain them, with monthly output reaching 6 figures. Quality control procedures developed by Bell Telephone Laboratories ensured remarkable reliability rates. Each fuse underwent 17 separate tests before shipment, including shock resistance trials, frequency accuracy verification, and sensitivity calibration. Field reliability exceeded 85%, extraordinary for electronics technology in 1944, meaning that fewer than 1 in 6 fuses failed to function as designed. The power source represented another breakthrough. Each fuse contained a miniaturized battery capable of powering the radar system for the brief seconds between gun firing and target engagement. The battery activated automatically upon firing, eliminating the need for external power connections that would have complicated ammunition handling procedures. Security surrounding the technology had been absolute. Even ship gunnery officers didn't understand the fuse's operating principles, receiving only basic employment instructions. Shells were delivered in sealed containers with strict orders that unexploded rounds must be recovered or destroyed to prevent enemy analysis. Japanese military scientists analyzing shell fragments recovered from failed attacks identified unusual electronic components, but dismissed them as primitive guidance systems. Their technical assessment concluded that miniaturized radar was impossible given vacuum tube limitations and power requirements. This fundamental misunderstanding of American technological capabilities would prove catastrophic when proximity fuses entered combat operations. October 14, 1944, 1400 hours. The first combat deployment of proximity fuses occurred as Admiral William Halsey's Task Force 38 faced the largest coordinated kamikaze attack of the Pacific War. Captain Robert Anders, commanding USS Stockton, received authorization to employ the classified ammunition that had arrived under maximum security just 3 days earlier. Japanese aircraft approached in the traditional formation that had proved devastatingly effective against American forces throughout 1944. Lieutenant Kenji Nakamura, leading 12 Zero fighters in a coordinated dive attack, had calculated his approach to exploit the reload intervals of American 5-inch guns. His tactics, perfected through months of successful kamikaze operations, assumed conventional time-fused shells that created predictable defensive patterns. At 14:03 hours, USS Stockton's forward battery engaged the incoming formation at maximum range.
Fire control radar had detected the aircraft at 18,000 yards, but gunnery officers waited until the targets closed to 12,000 yards before opening fire, standard procedure to ensure effective conventional shell bursts. The first proximity-fused shell detonated 67 feet from Nakamura 0 at 14:04:15. The explosion, occurring in empty air with no visible target nearby, initially confused both Japanese pilots and American gun crews. Within seconds, Nakamura's aircraft disintegrated from multiple fragment impacts, the pilot killed instantly by shrapnel that penetrated his cockpit from impossible angles. Combat action reports filed by USS Stockton's Gunnery Department documented unprecedented results. The first salvo of 12 proximity-fused shells destroyed 4 Japanese aircraft, a 33% hit rate that exceeded the theoretical maximum for conventional ammunition by factors of 10. Japanese formations, expecting to exploit gaps in defensive fire, found themselves flying into invisible kill zones that extended far beyond traditional engagement ranges. Radio intercepts by Fleet Radio Unit Pacific captured Japanese pilot communications, revealing their complete confusion. Shells exploding in air, no targets visible, aircraft destroyed by invisible barriers. These transmissions, decoded within hours, confirmed the psychological impact exceeded even the devastating physical effectiveness. Lieutenant Commander James Mitchell, serving as USS Birmingham's Air Defense Coordinator, witnessed the systematic destruction of Japanese attack formations that had terrorized American ships for months. His after-action report noted, "Enemy aircraft approached using standard kamikaze tactics. Our proximity fuses created overlapping kill zones that made successful attack impossible. 12 enemy aircraft destroyed, 0 American casualties." The mathematical superiority was overwhelming. Traditional anti-aircraft fire required direct hits or precisely timed explosions. Proximity fuses created spherical kill zones around each shell, multiplying effective target area by hundreds of times. Japanese pilots, trained to evade point targets, couldn't evade volumes of space. By 14:30 hours, Admiral Kurita's Northern Strike Force had lost 63 aircraft to proximity fuse engagements. Not a single kamikaze had reached its target. Japanese radio communications, monitored by American intelligence, revealed growing panic among surviving pilots who reported supernatural defensive capabilities. The tactical revolution was complete. Proximity fuses had transformed anti-aircraft warfare from a game of precision timing to systematic area denial. Japanese kamikaze tactics, developed specifically to overwhelm conventional defenses, became suicide missions with zero probability of success.
The psychological devastation inflicted by proximity fuses exceeded their physical destruction. Japanese pilots, who had courageously faced death in conventional combat, found themselves confronting an incomprehensible weapon that killed without explanation. Squadron leader Yoshio Tanaka, one of the few survivors of the October 14th engagement, provided testimony during post-war interrogations that revealed the complete breakdown of Japanese tactical confidence. "We approached as we had dozens of times before," Tanaka testified. "Our formations were perfect, our timing precise. Then aircraft began exploding in empty air. No shells struck them directly, no timing seemed involved. It was as if the sky itself had become hostile." His account, corroborated by other survivors, documented the terror these weapons inspired among pilots who had previously shown exceptional courage. Japanese naval intelligence, receiving reports of impossible American defensive capabilities, initially dismissed pilot accounts as combat stress reactions. Captain Minoru Genda, Chief Operations Officer for Admiral Ozawa's carrier force, filed reports stating that proximity explosions were impossible given known limitations of 1940s electronics technology. This intelligence failure compounded the tactical disaster. By November 1944, captured Japanese documents revealed widespread demoralization among kamikaze units. Pilots who had volunteered eagerly for suicide missions began requesting reassignment. The psychological foundation of kamikaze tactics, accepting certain death to guarantee mission success, collapsed when missions became certain death with zero success probability. American naval commanders documented unprecedented changes in Japanese behavior. Admiral Raymond Spruance noted in his November operations report that Japanese aircraft were avoiding engagement entirely rather than pressing attacks. This represented a complete reversal of Japanese tactical doctrine that emphasized aggressive action regardless of odds. The ripple effects extended throughout Japanese military planning. Imperial Navy headquarters, analyzing mounting pilot losses with no corresponding American casualties, began questioning fundamental assumptions about defensive warfare. General Yoshijiro Umezu, Army Chief of Staff, received reports that American technology had achieved capabilities beyond Japanese comprehension. Medical records from Japanese naval hospitals documented increasing cases of combat stress among surviving pilots. Unlike traditional combat trauma, these cases involved pilots who reported feeling helpless against weapons they couldn't understand or counter. Navy psychiatrists, unprepared for this psychological profile, struggled to treat aviators who described fighting ghosts and invisible barriers. The technology's secrecy amplified its psychological impact. Japanese intelligence services, unable to capture intact proximity fuses for analysis, developed increasingly desperate theories about American capabilities. Some reports suggested magnetic fields that could detect aircraft. Others proposed radar-guided bullets, all missing the actual technology by wide margins. American psychological warfare specialists recognized the opportunity. Radio broadcasts to Japanese forces began hinting at invisible defensive barriers and automatic sky mines that made attacking American ships suicidal. These propaganda efforts, based on genuine technological superiority, proved devastatingly effective against Japanese morale. The broader strategic impact became apparent by December 1944. Japanese naval aviation, the service branch that had achieved Pearl Harbor and dominated Pacific skies in 1942, effectively ceased offensive operations against American naval forces. The weapon that killed through proximity had created psychological distance that Japanese forces couldn't bridge. The proximity fuse's impact extended far beyond the Pacific War's conclusion. Military analysts from multiple nations studied the technology's decisive role in neutralizing Japanese kamikaze tactics, recognizing that electronics had fundamentally altered the mathematics of aerial combat. The weapon demonstrated that technological superiority could overcome numerical advantages and tactical innovation when the disparity became overwhelming. Post-war testimony from Japanese military leaders confirmed the weapon's strategic significance. Admiral Soemu Toyoda, former commander-in-chief of the Combined Fleet, acknowledged during Allied interrogations that proximity fuses had made our aviation tactics obsolete overnight. General Curtis LeMay noted that the technology saved thousands of American lives by ending kamikaze effectiveness without requiring invasion of Japan. The industrial implications proved equally significant. American proximity fuse production, reaching 22 million units by war's end, demonstrated manufacturing capabilities that Japanese industry couldn't match. Each fuse represented integration of university research, private industry innovation, and military requirements, coordination that became the model for post-war defense development. Dr. Vannevar Bush, director of the Office of Scientific Research and Development, wrote in his 1945 final report, "The proximity fuse exemplified how scientific research could be rapidly translated into decisive military advantage. The weapon proved that complex electronics could be mass-produced and deployed effectively under combat conditions." The technology influenced military doctrine for decades. NATO forces during the Cold War developed proximity-fused surface-to-air missiles based on principles established in 1944. Modern air defense systems still employ proximity detection, though using digital processors instead of vacuum tubes. The fundamental concept, creating kill zones around projectiles, remains central to contemporary anti-aircraft warfare. Educational institutions preserve extensive documentation of proximity fuse development and deployment. The Smithsonian Institution's National Museum of American History displays original fuses alongside testimony from both American developers and Japanese survivors. These exhibits demonstrate how technological innovation could end tactical stalemates that conventional weapons couldn't resolve. Contemporary military historians recognize proximity fuses as representing a watershed moment in warfare evolution. Professor John Lewis Gaddis of Yale University notes that the weapon demonstrated how industrial capacity combined with scientific innovation could overcome traditional military virtues of courage and tactical skill. The ethical implications continue generating discussion among military philosophers. The weapon's effectiveness in reducing American casualties while decimating Japanese forces illustrates the moral complexity of technological warfare. Some argue that superior technology reduced overall casualties by ending conflicts more quickly. Others question whether technological dominance creates unfair advantages in warfare. Modern precision munitions trace direct lineage to proximity fuse innovations. GPS-guided shells, radar-seeking missiles, and automated defensive systems all employ proximity detection principles pioneered during World War II. The miniaturization techniques developed for vacuum tube electronics became foundations for transistor technology and eventually microprocessor development. Today, the Battle of Leyte Gulf stands as testimony to proximity fuse effectiveness. The engagement where Japanese kamikaze tactics met American proximity fuses marked the end of Japan's naval aviation threat. In October 1944, liquid fire had cleared caves on Iwo Jima. By December 1944, invisible electronics had cleared the skies over the Pacific. The lesson remains relevant. In modern warfare, victory belongs not necessarily